Our presenter today for our 25th Sodick Friends webinar is Shane Vandekerkhoff from RJG. We're very excited to have Shane with us today. This partnership goes back long before I started with Sodick with RJG in our company. So always good to hear kind of what's the latest and greatest with molding technology and that sort of thing. So Shane is the Director of Consulting and Training, I believe, right now for RJG. Looks like 20 years of experience in the industry, all sorts of roles, customer support, business development, and now obviously the training and consulting side. So thanks so much, Shane, for being here with us. With that, I think I'll hand it over to Weston real quick to maybe go through the Q&A and how we'll handle that, and then we'll get started. So thanks everybody for joining.
Great. Thanks, Bennett. And welcome, Shane, and to our audience. Welcome to Sodick Friends number 25. Thanks for joining and making this webinar series such a great success. And we do have a few more lined up in the upcoming months here. A couple of weeks out, we have Ampeset, which is master batch and feeders, and then Fragile after that. So here today, looking forward to a great presentation, and as mentioned, we'll let Shane, I guess big thing is let's let him get through his entire presentation, and then we can address all the questions at the end. So if you would, throughout the presentation, please submit all your questions through the Q&A tab that's on the lower right hand corner of the WebEx screen, and address them to the host. Once Shane wraps up his presentation, we can fire all the questions at him and allow him to answer each one individually. And I guess, Shane, with that, let's turn it over to you and let you begin, okay?
Great. Appreciate it.
Thank you.
All right. Get fired up here. So hopefully everybody can see that there in presenter mode. So if you had joined us, you probably heard us a little bit talking about the new logo that RJG presented at the beginning of this month. And so if you see the new look, here it is, our marketing group. If you want to know more about how we came up with that logo, there is a pretty good video out there explaining how we came up with it. It's on our LinkedIn page. I encourage you to go take a peek at it if you're interested in how we came up with that. So I'm going to turn off my camera just throughout this, just making sure we don't have any bandwidth issues, and then when we get to the Q&A session, we'll pop it back on for you. So fundamentals of systematic molding. Some of you are probably very familiar with this if you've taken an RJG course before. We had systematic molding for years and years and years, and we went through a redevelopment of that course and launched it at the beginning of last year. And with that, we revisited a lot of the norms that we presented to the industry and as a messenger of certain methodologies, and those have changed. And so I wanted to address a few of those and show you some of these new best practices that we've implemented in the new course and kind of what's new. So we'll talk a little bit about RJG, the history of RJG if you're not familiar with us, talk about the fundamentals of systematic molding class, keeping up with the trends and customer demands. And a couple of those things that we're going to touch on are how we establish a fill-only part. This methodology has changed before. So if you're familiar with us, we typically say 95 to 98% full at transfer. That was done visually. We've applied some more math to this, so the approach is a little bit more systematic. And then we're going to talk a little bit about optimizing screw RPM. So these two things are probably the two largest pieces of information that are going to be different for you if you're familiar with the RJG decoupled molding methodology. So a little bit of history on RJG. It was founded in 1985 by the founder, Rod Grollo. You can probably guess where the RJG name comes from. So Rod is an industry veteran. He's been there for, close to over 50 years now. Rod worked with cavity pressure when he was working on his master's thesis way back in 1969 when he went to the General Motors Institute in Flint, Michigan. And so he did his thesis paper was on the application of cavity pressure sensors for a General Motors application. And so that was kind of the genesis of the company. And from there, it turned into consulting and training, cavity pressure manufacturing, and data acquisition as you know us now. Headquartered in Traverse City, Michigan. I'm a native there myself. I was born and raised just outside of Traverse City. And then I moved out to Salt Lake City for a decade and now live and work out of the Kansas City area. We have about 150 employees worldwide. 100 of those are located up in Traverse City area and then throughout the US and Europe and Asia. 80 qualified trainers. So we have a training and consulting program. So for any of you that would like to teach RJG materials at your companies, we have a program that you can come through and then you can become trainers for your own companies and provide fundamentals, essentials, potentially Master Molder 1 level courses for your own people at your own facilities. And we have offices and locations in 9 countries. And so here gives you a little bit of a map of where we are. And so we have Traverse City, we have training facilities also in North Carolina and now in Alabama. So we've recently have moved a couple of those locations. So our Woodstock, Georgia facility has recently moved to a Southern Union State Community College, and they're just outside of Auburn, Alabama. So about a couple hours down the road from where we were originally in Georgia. And our Gibsonville, North Carolina facility will be moving to a new facility in Kannapolis, North Carolina, just outside of Charlotte. And so that is another partnership with Rowan Cabarrus Community College. They have started a program. It's a brand new building, brand new build out just outside of Charlotte. And then we have training facilities at our RJG Mexico. Also, we have a place to host training at our UK office. Germany, France, both have training facilities, and then out in Asia, we are working on establishing a training facility out there. So spread pretty well throughout the globe. So if any of you are coming from international locations, you can kind of see where we're located. And if you need contact information, you can go to our website for any of those office locations and contact points. And of course, you can feel free to reach out to me, and I can get you to the appropriate people as well. So jumping into fundamentals, as I said, when we went through this as a rebuild, this kind of started with when we actually acquired a company in the UK that was formerly known as G&A. They had a very similar course to our systematic, and we worked with them and we rebuilt it and combined those two into what we now refer to as the fundamentals of systematic molding. So this would be a good course for anybody who is a seasoned molder, lots of experience, to sales staff, learning to trying to get more hands-on time. One of the big things that we had come away with when we started talking to our customer base was the need for more hands-on, right? Less classroom, more hands-on. And so we have done that with this course. We've added a day to it. So our previous course was 3 days. It is now 4 days. And about 70% of that is hands-on machine time. And so our focus for this is not so much process development as it is cause and effect. And so what we're focusing on here is when we do this on a machine setting, or when this happens, this is going to be the result of that. And so we start to learn the relationships between the machine and the material and then the outputs and what happens to the parts. And so that's kind of been our focus for this class, and it's been really, really successful. The feedback that we get on this is this was a great improvement to an existing course, and it's been fantastic. So the format of this is we usually cap this at about 12 people, and we have partnerships, so people will get together. During the pandemic, we had to take this down to 6, just so we could have social distancing and those types of issues. So it was 1 person per machine and 1 person per work desk. But we have eliminated the cap and we're back to 12. So we will have these scheduled throughout the year at any of the 3 facilities in the US and then at our international facilities as well. We can do this online. We have executed this as an online format in many instances, either public or private. So sometimes we will do this as a public event where you can come to us. We host it as a webinar or more of a course structure than more interactive than you would normally see over a webinar. And then we have remote lab sessions to support the course content to try and provide some of that experience throughout the class. We can do this as a private event as well. So if you had a company, you wanted to do a big, large group of people, then we can do that. We just are in the midst of doing a very large online training of 150 individuals across 3 shifts. And so that's all going to be done online. So I know that with the labor shortage, people are struggling to get people out to training events because there's a lack of coverage. And so that is an option that we can provide if it fits your needs. So to jump in with this, one of the things that you'll also see in the fundamentals class is what we refer to as a 32-shot capability study. And we typically would do this towards the end of the class. Sometimes we do it at the beginning and at the end of the class to show any kind of improvement that we have. And what we're doing is this is just a single cavity mold. It's a part weight study. And what you'll see is we just weigh 32 consecutive shots. We're taking those averages and differences and we're doing some math on it. And what we're finding down here is an average, an upper limit, and a lower limit variation. And what we're looking for here is a variation of less than 0.4%. And so that was kind of established as an industry standard in SPC circles. It's closely related to, there's a direct relationship to Six Sigma, or, lean manufacturing practices and Six Sigma, 5 Sigma, 4 Sigma, those types of things. And so we apply this, and what it just gives you a little bit of exposure to what's repeatable, right? What does it mean to have a process that is considered to be solid? We can challenge it in some ways. If you'd like to challenge it, we've done that in our courses before. Maybe we throw a little viscosity change at it. We can add colorant, we can do other things, and we can do this in multiple formats, if you will, and kind of test and see how the results come out. So pretty straightforward. Again, if you have high cavitation, this becomes a little bit more difficult than if you're in that 2, 4, 8 cavity range. If you're doing 128 cavities, then catching parts becomes a little bit more of a difficult task, but can still be done here. Let's see here. Here we go. The next thing that we kind of do too is this. Again, this is a cause and effect on shrinkage, and so on day 3 of the course is typically where we do a lot of work with, hey, let's show the difference between a semi-crystalline material and ABS. And again, this kind of goes to that cause and effect theme that we're working on. Is we talk a lot about shrinkage in semi-crystalline materials, not as much shrinkage in amorphous materials. And here is the goal of this is to demonstrate what that does. And so we go out, we run an acetal. It can be polypropylene, it can be high density polyethylene, just some type of semi-crystalline material. And then we run it against an ABS. And so that's what we're kind of seeing in these 2 examples. Again, we take shots, we measure the pressure for reference, cushions, part weights. And here we're doing some fairly simple measurements. We're doing a length, we're doing a width. We don't want to have too complicated, when it comes to the measurement process. We like to try and keep it as simple as we can. And typically we're just using a pair of calipers to measure these length and width. And we compare that against the steel dimension. So we have the steel information for our tooling, And then we punch that in, and then we measure the measured part length, and then we document it. And then what we do is we come back the next day and we do another measurement. And so we're comparing those between two different time frames typically. And you can see the shrinkages that come across, right? Shrink percentages, you have the overall, you can see the lengths and widths between two different parts. And the other thing we do is we also apply colorants to this. And so you can see what the effect of colorant has on these materials. And so we can color the POM, or we can color the ABS, and we'll use reds and blues and purples, and we can use pretty much whatever we can get our hands on for the colorant. But you can see the difference between a natural material and a colored material and how that affects shrinkage. Is it more? Is it less? And you can really start to understand what the effect of these different materials and the different colorants have when we're looking at shrinkage data for these. And it's not something that we've done before. So this is new, and it's also been very powerful for people to really understand. We talk a lot about it, the difference between shrink rates in these materials and different colorants, but now here's the opportunity for us to really put the rubber to the road and show it with hard data on what the effects are and what the changes are. And again, this is all done on the machine, and this takes some coordination to do. We've got everything set up to make this go as smoothly as possible, but it's a fun little exercise that people use during the course time. Probably one of the most significant things here that we'll talk about is the fill only. As I said, when we kind of got going, was what's the effect of it? We've talked about establishing 95 to 98% fill only parts. This is visual, and what we're going to kind of see here is how we've changed things. Traditionally, we had used the rheology curve. So if anybody has taken a course with us, you run fast, you run slow, you have a plot that gets done. It goes from left to right. It starts out high and then works its way down to a flat, more stable portion. And so the theme there was, well, when we set a fill only part, we want to select a fill speed that was on what is quote unquote known as the flat portion of the curve, right? So that was a best practice. And we're no longer using that. And there's a few reasons behind that. One is a matter of scale. So for example, if we talked about two different machines and we're trying to establish a universal flow rate. So for example, if we use a couple of machines today are going pretty fast. We had some new machines, we have some older machines. If we take the Sodick, for example, that we have in our Traverse City lab, a fairly robust machine, injects pretty fast. And we had an older machine in there, not very old, but max flow rate, I think, was about 5 inches per second, something like that. And so what happens is if you ran a rheology study on a high performance machine on the Sodick, and then we went to this older machine that didn't have as equal as performance, and we were on the Sodick and we say, hey, this is the flat portion of the curve on the Sodick. Well, if I move to the other machine, that other machine one may not be able to achieve that rate. And then it's going to move it out to the even flatter portion. Now, if you go the other way, if we started on the lesser performing machine and we chose a flat portion on the curve, as we used to call it, and we transferred it to the Sodick, well, all of a sudden the flat portion now becomes the elbow of that curve on the Sodick because the Sodick outperforms. And so you appear to be in what had been referred to as a flat port or a unstable portion of the curve where material viscosity could affect your process. And so there was a lot of confusion and misinterpretation of the data when using that. And when we kind of looked at it from a historical standpoint, the rheological properties of material, the shear thinning, what it does when we mold it. When Rod was teaching in the field and doing consulting, that was kind of a foreign concept. That when you slowed down, the parts got smaller due to the thickening viscosity of the material. And so it was a tool that he had used to demonstrate that effect. And it evolved into something that it probably wasn't meant to be evolved into. And so we've pulled back on that. And so we're using a weight method, and basically our focus is going to be on part quality. So it's very similar to what we've done prior. We go from fast, we go to slow. But what we're focusing on here is what do the parts look like versus just the flat portion of the curve. And that was kind of getting lost, right? Fill as fast as possible, consistent with quality, is the message that we want to send. And so when we look at how we're doing this today, we're setting the pack and hold pressure to 0, which is normal. One too many clicks. Which is very normal. That's consistent with how we've done it. Time, we typically leave the hold time on. There are some things that you will see with some machines, nuances, if you will, where time has to be set to 0. We kind of take those as a case-by-case basis. So we're going to adjust the V to P transfer position, right, as we transfer into second stage to produce a reference shot where the part is actually 100% visually full. It's very sinky. We are not applying any second stage pressure, but you've basically had filled all the cavities. It has sink marks. We don't want any flash on these parts. And then what we do is we weigh this reference shot, right? No runners, just the parts themselves. And then what we're doing is we're multiplying that by a percentage, right? And so in this case, we take this 100% full part, we multiply it by 0.99, and that becomes our target fill weight. So if it's 100 grams, we multiply it by 0.99%, or 0.99, I should, 99%. And what you get is a shot that looks like something up above with these two cavities. So we have the cavity, on the left is more full than on the right, but we have what would be considered a short shot on the right cavity, and this would be our fill only. Now, we have a part weight now, so we have the systematic approach. We've got a mathematical approach to it, and we can apply this to pretty much any part around the world. It doesn't really matter. We've done thick parts, thin parts, and we've had a lot of success from this. So it's a departure from what we've done before. We've always said 95 to 98% visual. Now we're saying 99% full, based on part weight. And you can see what that looks like. And so once we've done the math, we need a 99-gram fill only part. What we're going to do is we're going to adjust that V to P transfer position until that is achieved. The other part of this is also going through, this is kind of, we've gone through and established kind of where our fill only speed is. So the fill only, the flow rate, when we're establishing that, is from a high to low, just like we did when we did rheology curves. We start high at the fast fill rate, and we start to just slow down. And what we're looking for on our parts is at the high speeds, do we have any burning that might be occurring? Do we have any, gas trapping? What are any kind of visual defects that I can see? And we just continue to run down to the slow fill speeds, and we are just looking for any potential quality defects during that procedure. And I'm going to share that with you guys when we get to the end. It'll be a handout that you can download. I'm hoping that we can share it with you through the platform here, and that'll be a takeaway for you. The other thing when we dealt with rheology curves is when we slowed down, the parts got smaller, and what we wanted to do is we wanted to get away from that. We wanted to show, what is the effect that fill speed has potentially on the quality of the part when it's going to be full. Now, to do a rheology curve, you really couldn't change the size of the fill only. So your shot size and your transfer had to stay the same throughout that test. In the new procedure, if you want to, you can increase the shot size or decrease the shot size while you're doing the test hey, this is what, when I fill it 1 inch per second and the part is 99% full, this is what it looks like. And if I fill at maximum speed, I can adjust the shot size or transfer, and this is what high fill rates look like when I'm dealing with this. So it gives us a little bit more flexibility as well when we're going through the optimization and establishment of this process. We're not constrained by the rheology curve and having to get good data to be able to continue to maintain the shot size and the transfer positions. There's still good usage and for the rheology curve. A lot of that data is transferred to the new procedure. What's your maximum fill pressure? Especially if this mold is going to be running in multiple machines, we need to know if all of our machines are capable not only of fill pressures, but also of flow rates. So we have a table of data where X machine is capable of 30,000 PSI and this mold is only taken 20. Those types of concerns. What's the flow rate across those? Volumetric flow rate. We're tabulating all of that information. So when we get to a position to where molds need to be transferred, it's as robust as it possibly can be. And we're adding this piece of it, this mathematical approach to setting the fill only by part weight. We're adding this to it as, again, we're trying to add more consistency to it and making it more robust. And so there's less discrepancy between maybe one processor to the next. And so that was our approach to this. And so far it's proven to be quite successful. We see it to be a little bit more repeatable. We have done some experiments in classes where we will have 2 different students do the procedure, and then we compare the size of the fill onlys between the 2, and we're seeing more consistency. And so that's good, right? That's what we want to be able to do. The next thing that we're going to notice here is in optimizing the screw RPM. So this is another pretty big departure from what we have always kind of said, or the message has been. And we have typically said, if anybody has been through any of our coursework, we have typically said in the past that what we would like to do is slower is always better, right? Slow as possible without extending cycle time. We have to have so much, maybe a little screw run delay in there, and a little bit of time before mold open. And when we've kind of changed this messaging, it is more so material dependent than just a blanket statement. We're implementing shear rate calculations. So this has come out of our office in the UK. John Goff was the gentleman that had started the company. And when he was at university, very similar to Rod, he did shear calculations and on screw rates and RPMs. And so it was I don't know if it was his thesis, but it was a class that he took, and the data that he provided that provided the basis for the information that we're about to share with you. And we want to focus on the circumferential speed, right? And so not necessarily RPM, but we want to look at feet per minute or meters per second or whatever unit of measurement we want to look at, but away from RPM into a more universal circumferential speed. And so with that, we've come up with a table. Now, this is just a snapshot of it. This is not everything that is included in this table. But you have some material on your left-hand side, the dryer times and temperatures, And then we have screw surface speeds. This is in inches per second as a unit. And then we have a correlating RPM. So if we just take ABS for an example, minimum screw surface speed is about 18, maximum 25.6. And what that means is to correlate that to RPM, if you have a machine with an 18 millimeter screw, that would be 583 RPM. And you're like, holy smokes, right? I'll never achieve that. And you're probably right. Polypropylene is another one where some of the material is you can't achieve it. If you look at this HIPS that's down here, this HIPS FC, they're talking about on small screws 1,000 RPM, right? Well, no machine that I know of even approaches that. And so when you look on the really, really small screw sizes, those RPMs are astronomically high. But when you look at screw surface speeds in the inches per second, as the screw size moves up, you'll notice those RPM numbers go down. And so if you're running smaller machines, and these are based off shear rate calculations, right? So if you have a high RPM, basically what we're looking at is it's relative to how sensitive to shear it is. Now, if you run into a machine that's got a 50 millimeter screw or 100 millimeter screw, as the tonnage goes up and the screw diameter goes up, what you're going to notice is that we've got those RPMs will continue to go down. And so for us, at our training facilities, most of our machines are in that 50-ton range. We don't have anything very large, right? And so most of the machines, when we're running ABS or polypropylene in classes, the RPM recommendation is higher than what the machine is capable of running. Now, if I go to a customer, and this recently happened, they're running a 1,500-ton molding machine, they're running an ABS. This number is easily achievable. These screw surface speeds are now in the 30, 40, 50% range on larger machines. And so this, again, is a very big departure from what our messaging has been in the past. Now, I don't think we have any glass-filled materials in here. But if you look at the worksheet for a glass-filled material, these RPM recommendations are going to be much lower because we can't damage the glass. And so how do we set this up? Well, now that what we're looking at and what we're seeing is higher recommended screw RPMs than in the past, the question has become, well, what are the rules now for getting the screw back? Well, we always have said, 1 to 2 seconds before mold open. We don't want the screw RPM to dictate our cycle time, so we want to make sure that screw is returned to the shot size before the following shot. And so what we do here is we just run screw run delay before rotation. And so if I have let's say for a scenario, let's say my cooling time is set for 10 seconds, but I have 4 seconds of recovery time due to a higher RPM. Well, I would just simply add 3 seconds of delay at the beginning, pull the screw back 1 to 2 seconds before mold open, and then fire the next shot. And so those are some of the things that, we have drastically changed in the way that we approach some of these best practices. And if you're familiar with RJG, or if you're not, for those of you that are familiar with us, have taken us courses, you will notice that this is a pretty big departure. And so we're really just trying to show that, over time you gain knowledge and you have to review your norms and best practices. And these are the big things that we've come up with in regards to how that affects your molding process. And how do we, continue to address customer needs and keep the content up to date and moving forward. So those are some of the big changes that you're seeing in the fundamentals. If you go through some of the other courses beyond fundamentals, we have Master Molder 1 and Master Molder 2. You're going to see these kind of go into those classes as well, but the approach to those is going to be a little bit different. Here, what we're trying to do is in the course is we are trying to show cause and effect, and with a little bit of optimization, right? We're not really at this point focusing on the optimization of the process. We have what we refer to as a decoupled workshop, which is a hands-on workshop that is after this, and then that's another 3-day course. That's more optimization. The other thing that we have removed from the fundamentals class, if you've taken some of our courses previously, is we had a lot of information about machine performance and evaluation. These were speed linearity, check ring studies, those types of machine performance have been removed, and they've been introduced in the decoupled workshop because that's where we're starting to get into more of the actual process development and focusing on how does process optimization and how can that be affected by machine performance. And so we introduce it in there. And then of course, when we get into the Master Molder 1 and 2 level courses, again, there's another level of understanding there and optimization there. So that's kind of the progression that we work through. Most people start here and then go to the workshop. And then if you want to come into Master Molder 1, Master Molder 2, again, we hold those courses throughout, and you can reference our website too at any point in time to get some of that information. So those are pretty much the highlights that I kind of wanted to cover today. We get into some of the Q&A sessions at this time. I'm going to turn it back over to Weston at this point. I'm going to stop my sharing and turn on my camera. If you'd like to have any questions, we'd be happy to answer those. In addition to that, if you need towards the end of this, I'll show you some. Well, I can probably let me get this back up here. I probably quit too soon. There's information in regards to our courses. My information is here. There's a QR code. You can take a snap of that on your phone. I believe the presentation can be shared. If you'd like a copy of it, be happy to share that as well. My information is there. You can feel free to email me, give me a call, text message. The QR code will take you to our website and our training schedule. You'll see everything on there for the United States and Europe training schedules and availability. So we also show you how many seats are available and when they are. So I think our schedule has been released for the rest of this year anyway. So if you have any questions in regards to that, you can reach out there and see it at that point. So.
Excellent. Thank you, Shane. What a lot of great information there today. So, and we had a number of great questions come in already. So let's just jump into them, I guess. In the intro, I know you had mentioned that there's a 4-day seminar.
Mm-hmm.
Will you be sending out information on that, or maybe talk a little bit?
Yeah. So the 4-day fundamentals class it's Tuesday through Thursday. They are located at RJG training facilities. So Traverse City, Michigan, Gibsonville, North Carolina, which is outside of Raleigh-Durham area. And then also at our Southern Union State Community College, which is down in Auburn, Alabama. So it starts on a Tuesday. Typically what we have there is we've got we go through a little bit of classroom and then we go out to the machines. And what we do is in our coursework, we provide basically self-guided instructions and exercises. So when we get to those, we're going to go out there, we're going to do a melt temp study, we're going to establish RPMs, we're going to establish fill onlys, and the students are really following the instructions. We have 2 people in our lab that guide the students there. So we have a primary instructor and we also have a secondary instructor. They're there for guidance and coaching, and that's kind of the format throughout those 4 days. Wednesday and Thursday are almost entirely on the machine and hands-on, and then Friday we have a little bit more classroom, and then we're excused. But I can share those schedules with you again. If you can scan the QR code, or you can go to our website at rjginc.com, and we have the full schedule there available to anybody.
Great. Great. Why was the rheology curve removed from the process of selecting fill speed?
Yeah, I kind of touched on that a little bit. One of the things that came up in our own discoveries, if you will, was in our classes, we found that a lot of times the intention of it was misinterpreted. And in our Master Molder 1 and 2 courses, we have to do a process development and then we have to do a process match. And so a mold has to be moved to a second machine. And what was being missed was the machine capability portion of that. And students were either overbuilding or underbuilding, I would consider the process. So if we went from machine 1 to machine 2, the second machine was unable to achieve the flow rate or the fill speed. And when using cavity pressure, and one of the grading criteria that we use is to match it within a certain percentage. Well, if you didn't establish the fill rate correctly, then you couldn't achieve that. And so the thinking was, well, if they're missing it here, how often does it get missed at the customer? And so that's where we kind of had to get into pulling back and changing the message and really focusing on part quality and robustness in the building of the process and of the fill only part. So that was kind of the reason we got away with it. And I think I mentioned the original intent of doing a rheology curve was never really to establish a flow rate or a fill only part size. It was really to demonstrate the shear thinning effect of plastic. And so with that in mind, we kind of pulled back on the use of it and kind of used a different methodology to do that.
Excellent. Shane, can you relate this discussion a little to the theoretical side? Are shear rates and shear flow in the barrel straight contributors to material degradation to shear?
They can. Yeah, they can be for sure. So when we look at shear rates, and here's one of the other things when we talk about shear rates is that there's not a singular shear rate in a molding system. We have shear rates in the barrel. We have shear rates through the nozzle, through the runners, through the gates, and through the cavities themselves. There is a time component to shear rate and degradation. And what I mean by that is you have shear rates through the gate, for example, are typically quite high, but the material doesn't experience that shear rate for a very extended period of time. Now in the barrels, you've got all of that material being sheared for whatever that recovery time is, 3, 4, 5 seconds. And so there's an optimum level of shear rate. So obviously we have to melt and mix and prepare that material. And so that's where the data is coming from is here's the established shear rates for the material, what it likes, what it doesn't like, and we're providing the upper and lower limits for basically those types of those materials so that when we shoot it, it is in its optimum state, right? We want to make sure that it's well heated, well mixed and prepared to shoot. And so that's kind of the reason for it and where it comes from. Now, when we talk about shear rates through the nozzle and gates and those types of things, that's more of a filling speed issue rather than a rotational speed issue. And so they're kind of separate things. And PVC is probably a really good example for those that have run rigid PVC. It's very shear sensitive. RPMs need to be slow, and so do your flow rates need to be slow. Where if you're running a HIPS, it's a very robust material, and I can have high shear rates and high flow rates because I don't have to worry about damaging it as much as a rigid PVC material would be. Hopefully that answers that question.
And there's a second portion to this, and maybe I missed it here. Did this used to be part of the older pack and cool analysis to detect nonlinear shrinkage, in flow direction and transverse to that?
We didn't really look at it from my understanding from that context, right? And so when we when it comes to the shear rate, I can't say that this was basically just what's happening in the barrel, right? And so we didn't look like the effective shear rate on shrinkage at this point. And so, I mean, it's something we can obviously do, but that was not a part of the recommendation on this. It is going to be, when we look at the shrinkage, with the direction of flow or perpendicular to flow, it's so dependent on where's the gate located, where's the material, what's in the material, how many gates do you have, and so it wasn't a part of that. These recommendations were not a part of that, and for considered shrinkage wasn't considered as part of these recommendations.
Great. Next question for you here. How would we adjust the size of the fill only part for multi-cavity molds?
That's a good question. That comes down to cavity balance and part concerns. And so what I mean by that, if you're running 32 cavity or 64 cavity or high cavitation tooling, I showed you a 2-cavity mold, which the cavity balance is going to be very similar anyway. If you're running high cavitation tools, that may not be the case. So what do I use as the reference? You can also adjust this, right? And what I mean by that is typically what we would say is we typically use the most full cavity. And the reason for that was flash. I didn't want to overfill the tool and flash it. We've traditionally run caps and closure molds where we've run into caps and closure molds where we have completely full parts, and then we have what's commonly referred to as a poker chip, right? It's just the round top of a cap. And so we've got this big imbalance. And so in that case, what we would do is we'd recommend something that was in the middle, right? What was the average? With this methodology, because we're using a part weight, you can still fill it to 100%. And then, if you're seeing flash, then we've got to back off until we don't see flash. And then what we do is we still apply the 99%. And so it's definitely more difficult. You can use the most full cavity. That's been our recommendation in the past. And what I would typically recommend if the balance is way off is use something in the middle. Is using an average representation of all cavities seems to work much better in those cases.
Wonderful. When a hot runner tool is in use, especially if direct gated, right? Are there any of the process development steps that need to be altered?
Good question. We don't typically. Now, the one thing that we would do in a hot runner is when we tackle cavity balance. Typically, when we're running cavity balance studies and we're looking for how our cavity balanced is, if you got direct drops, we can thermally adjust the balance. Now, that would be a secondary step. So typically what we recommend would be to set your tips at the barrel temperatures as a starting point. So if I got a 500-degree barrel, we set the tips at 500 degrees and test the balance. Now, what we can do and what we have seen that can improve on balance with a hot runner system is to start elevating your tip temperatures. And so what we'll see is you might see your tip temperatures at maybe 520, where your barrels might be 500. And we've seen that improve balance. In the thinking behind that is this: the barrel, the 500-degree barrel temperature, has got a lot of shear occurring with the screw RPM, especially with the higher RPMs that we're using now in the recommendations. When the material is in a hot runner system in the manifold and the tips, it doesn't have that shear going on, right? It's essentially sitting there, and so all of the energy has to be through electrical heat to maintain that temperature. And so you probably are losing some of that temperature through just atmospheric conditions, passing it on to the platens. And so what we're seeing is if you elevate the tip temperatures to make up for that loss in shear while it's sitting there, we actually see an improved cavity balance with a hot runner system. So that's an optimization step that would be a little bit different than if you had a cold runner is you can start playing with your manifold and tip temperatures and see how that affects your cavity balance in a hot runner system.
Excellent. Shane, does the 0.4% on the 32 shot capability study, does that relate to Six Sigma?
It does. I'm trying to remember exactly what the numbers are here. You know, when we talk about it's, I want to say that it's 4 sigma when we look at it from a percentage standpoint. So there is a direct relationship between the 0.4% and a level of sigma.
Excellent. How do these concepts work with micro parts that may weigh less than a milligram?
Yeah, it's a good question. To be quite honest, we don't have a lot of experience in that area. And so I really don't have enough data to go on to tell you, you know, these things work really well, these things don't work. It's the same for if you're an LSR molder, you know, it's a completely opposite type of process. And so a lot of the things that we talk about work and some of them don't. And for micro molding, when we get into that sub-gram part weight, unfortunately, I just don't have enough information to provide, you know, what really works well and what doesn't for those applications.
Are there concerns for air voids entering through higher RPMs?
We haven't seen it. There's also a piece in there about back pressure optimization. And so with the RPM, one of the things that we want to do too is make sure that the back pressure is sufficient enough to make sure that we could have good repeatable parts. And so there's a back pressure optimization study that we can apply and start out low, 200 and, you know, maybe PSI back pressure that's specific, and work your way up. And then what we're looking for there is we're looking for the most repeatable part weight. So if you take 5 samples, I want the lowest variation between the samples. And so we use back pressure to make sure that we have enough to make sure that we're squeezing any of the air out, and we're getting good repeatable parts. So that's kind of the second part to that we can apply to make sure that we're not getting air. And we would look for it too, you know, as we're building out the process. If we're seeing what appear to be air in there, then we know that we'd have to go back and adjust, most likely either back pressure. If we do see what we think is air or gas, that might be a degradation issue. Maybe there's something in the material that is off gassing. And so if we slow down, then maybe we would see that go away. Air, we haven't seen to be a problem, but it could be something else. It could be a gas that's coming out of the material of some sort.
Can you contrast barrel effect and shear with respect to hot runner systems versus cold runner systems? So is material degradation due to shear higher, or is it just that the hot runner invites thermal degradation due to heat history?
It's mostly heat history. Now, it's a pretty, I mean, it'd have to be in there for a very long time, you know, for heat degradation to occur. So a lot of times if you see, and sometimes material processing guides or design guides, they'll refer to hold up time is usually what they refer to it. We refer to it as residence time. And they'll have some kind of recommendation, a minimum of like 3 minutes, maximum of maybe up to 15. And that's going to be very material specific. But usually, you know, when we look at it, the runner sizes in a hot runner manifold compared to a cold runner manifold, depending on how many cavities, is probably a little bit larger throughout the system than a cold runner. And so shear in the runner system would be less. Now the gate size is a different issue as well. But usually it's not, you know, we don't have what I would consider to be shear related degradation any more in a hot runner than we would in a cold runner. If anything, if you had long cycle times, and we're talking minutes, where you might have thermal degradation. But I've run rigid PVC parts, 18-inch elbows, half-inch thick, cycle times 3.5 minutes, and we're not seeing the problem. So, and that would be a cold runner application or hot sprue. But so it would have to be a pretty extreme situation, I think, if you had any additional degradation in the hot runner. I think it would be thermal, but it would be a pretty long time that you'd have to hold it in there.
Excellent here. Maybe Shane will give him just a couple more minutes. That's into the questions that have been submitted. So
Okay.
we'll see if anything is coming in. Wanted to take a minute and say thanks for all the knowledge today. And thank you to everyone here who has joined in and enjoyed this presentation. So.
Well, I thank you very much for the opportunity and look forward for something else comes up in the future. I hope we can contribute. So thank you very much for hosting and having us today.
Yeah, great job, Shane. Really appreciate it as always, and great happy for the long relationship we've had together and a lot of shared customers. Keep it up in the future. Thanks again so much.
Absolutely. Thank you.
Thanks, everybody. Thanks for joining.
Thanks, guys.
Take care.
Bye-bye.
Okay, bye-bye.